All right, the air conditionata is working, and we are very happy. We can even make it a bit stronger. Anyway, tonight, Speck&Tech number 86, a long, long journey. For the people that are here for the first time, who's here for the first time? Can you raise your hand? Okay, not that many. Very quick. Speck&Tech is an association, is an APS, Associazione di Promozione Sociale. We were born almost 10 years ago, and since 2016 we're making events and gathering about technology and innovation. We meet every single month, even more often sometimes, and we're building a community. And this is our family, this is our community, people that are interested and love technology and innovation. Started in this very space in 2016, and as you see, we were like 60 people. And then we scaled up and we became 100, and then we gathered in the even broader spaces like Muse, and even broader spaces like Auditorium di Lettere. And then we moved around Trentino and we went to Rovereto. This was almost a year ago now. And again to Muse. This was last December, where we discussed about death, digital death. So what's the key point of Speck&Tech and how the format works? We discuss about a topic. The night is about a topic, and tonight we talk about quantum. And we tackle this from different perspectives. There are a number of talks, generally 2, sometimes 3. And at the end of the night, there's a networking part. Beer, speck, focaccia, whatever you like, carrots, anything you want to drink and to drink and to eat, of course. And meet new people. People that are becoming maybe your new friends, your new colleagues, maybe joining a project, a startup, a company, and getting out of your comfort zone and meet new family, friends, and people that you would like to discuss things. So, after a long journey, we came to Speck&Tech number 86, and tonight we titled it, and this was Michele's idea, Qubit or not Qubit. An applause. Okay. Anyway, 2 speakers tonight, and the first one is Federica Mantegazzini from FBK. An applause.
And the second speaker for the night, ENRICO BLANZIERI, professor from UTN. And this is not the first time that we talk, well, you might have guessed from the title, we are talking about quantum technology, and it's not the first time. We did an event on quantum computing almost 3 years ago, feels like yesterday, and we had different topics then. We had Davide Pastorello talking to us about quantum machine learning, or machine learning using quantum technologies, quantum computing. We had Niccolo Leoni talking to us about privacy and quantum computing, so things like quantum key distribution, cryptography using quantum technologies. And as you might notice, we were in this very space where we started in 2016, and we keep coming back here in Impact Hub, which is a very welcoming space. It's a space that allowed us to grow, to keep doing our events. And we do have a little partnership with them because they want to be very welcoming to the Speck&Tech community. So in case you're interested in a space to work here in Trento, in case you like this space, or maybe you want, they have also other spaces around Trentino, you might want to have a chat with Federico over there. So later, he's the hub manager. You can talk to him and find out what they can offer to the community of our speakers exclusively. So many thanks to Impact Hub for continuously hosting our events and our community.
And giving us the freedom to slice speck and cut cheese easily.
Yeah,
that is not something that you might not expect, but it's very difficult if you're going here and there, and then, you know, we're giving you a room, but yeah, you need to be careful.
We had improvised kitchens in the most unexpected places. Here we have a proper kitchen, for example, which is great. Anyway, we We have a website where you can find all the information about what we're doing, our next events, and also the archive of all the events we did from 2016 on, all the 85, 86 plus events. And for each event, you normally have the slides, you have the full video recording of the evening, and so you can relive our past events, or you can find information about a topic that maybe you missed, and now it's interesting. On the website, you also find job postings from our sponsors. Now we have the fresh job postings from the retreat. And if you maybe have a company and want to put your job posting here, come talk to us. We are open to sponsors. And also you find us on all the socials, of course, all the main socials, YouTube, Instagram, Telegram, LinkedIn. The handle is Speck&Tech. And tomorrow morning, you will receive an email if you have a ticket for this event. The email is about telling us a little bit about how the evening went for you, what went well, what could have gone better. So the air was too hot, the air conditioning was not great, or the beers weren't cold enough, or the spec was not enough and it finished very quickly. So anything like that, and whatever you can tell us. We do really read this feedback. So tomorrow evening, or probably next Tuesday, every Tuesday we meet and we go through the feedback for the events. We read every single one. We don't reply because it's anonymous, but we read. I assure you, we read every single one, and it's very important. It's what makes our events always better. What else? Right now, what you can do is scan this QR code or go to slide.io and put the code Speck&Tech. If you're used to our events, it's always the same. Here, you can ask questions to the speakers. And if you don't have questions, go there anyway, because you see all the other questions and you can vote the most interesting ones, and we take that into account when we do the speaker Q&A at the end. So that's all the information we have for you right now. And warm applause for our first speaker, Federica Mantegazzini.
I'm going the wrong way around. Yes. Okay. So thanks to everyone to be here, and thanks a lot to Francesco and all the organizers. It's really a pleasure. I didn't know this community, so for me it's the first time, and I'm sure will not be the last one. So today we talk about quantum, and in particular quantum computers. And my talk is a little bit a warm-up to tell you really how to build one. So my goal is to give you a building instruction, so you go home and you can build your own quantum computer. So let me introduce myself. My name is Federica Mantegazzini. I'm an experimental physicist. I studied physics at the University of Milano Bicocca. I'm originally from the Milano area. And then I moved to Germany for my PhD, where I started to work with quantum sensors, back then for particle physics and neutrino physics. And then I moved more and more into the realm of quantum circuits, and in particular superconducting quantum circuits. So I'm biased, and I will tell you mainly about superconducting qubits, because they are the best ones. And I also like cats, as you can see from the slides. And we will talk about a particular cat, the Schrödinger cat, again during the slide. Good. So let's start with this picture. How many of you have seen something like this? Perfect. All of you, basically. So that's the Google quantum computer, and this picture is from 2019. The date is not a random date, but it's the date when the researchers team of Google was publishing a paper where they claimed the so-called quantum supremacy, or today we like more to call it quantum advantage. So they show for the first time that with a quantum computer, they could solve a specific task, a specific problem that with a classical computer would have taken so long that was basically infinite time, so basically impossible. Now, when you look at this picture, I remember some friends of mine were telling me, but you know, this doesn't look like a computer. And I mean, they were right? I mean, it looks kind of messy, a lot of cables, a lot of crap around. And then I like to show you also this picture. This is what is widely considered the first classical computer built in the 40s, the ENIAC. And you see some similarities, right? Also, this one didn't look very much as a computer, but nowadays, 8 years later, let's say the grandchild of that ENIAC is the laptop that you have at home. So the take-home message here is that we do have quantum computers. They do exist actually already since 10 years or more, but they're still prototypes. They are laboratory prototypes, not optimized, with very little standards, and that's something where the community is working a lot to find some standards, and we do not know how quantum computer will look like in 80 years, 100 years, and so on. So they're anyway, difficult objects, laboratory objects, that are not easy to make and not easy to operate. Okay, so that's the first take-home message that I want to give you. But let's go back to this picture. So now we do an exercise of backwards engineering. So we start looking at the picture and we try to understand how to build it, okay? So first of all, what you see, most of the picture is not the computer. That's just a refrigerator, it's a fridge, a very expensive one. It's order of €1 million or something like that. But it's a fridge, simply because to work with the superconducting circuits, for those of you who know about superconductivity, we need to go at very low temperatures. We have certain metals, certain materials, not very crazy one. For example, aluminum is what we use every day in our laboratories. Aluminum is a superconductor, but it becomes a superconductor if you cool it down below what we call critical temperature. For aluminum is 1.2 Kelvin. So we need to go much below 1.2 Kelvin such that our superconducting circuits work actually as superconductors. And that's why we need a fridge. Sorry, wrong direction. So the scale, this fridge is pretty big. This is me with the similar model. It's exactly one-to-one, but it's not the Google one. It's the one that I used during my PhD at Heidelberg University. But you see, this is like big like that, and tall maybe 2 meters or more. So it's a big piece of hardware, just to give you the scale. And this picture that you always see, it's the fancy one where you see everything that is inside, but when you operate your fridge, you need to close it. Because since it goes to so low temperatures, obviously it cannot be in contact with the environment. So if you go into our lab or the Google lab or whatever, and you see one of these fridges operating, it looks like that, so much more boring. And that's why this is never the picture that they show on websites, but that's how it is when it's actually cold. So, how cold? Probably all of you are familiar with the concept of absolute zero. So the lowest temperature that we can reach according to physics. This is minus 273.515 degrees Celsius. And we use another scale, the Kelvin scale, where this is just 0 Kelvin. So absolute zero is 0 Kelvin. And then, if we look at our fridge up there, you see that we have different stages of refrigeration. We go from the highest one, that is what we call room temperature, 300 Kelvin, so basically the temperature of a room, let's say about 25, 26 degrees. And then we have a stage at 50 Kelvin, 4 Kelvin, 700 millikelvin. So millikelvin means we are 700 milli-degrees Celsius above the absolute zero. Then we go down at 100 millikelvin, and then the coldest part of the fridge is this one here, what we call mixing chamber plate. Mixing chamber because the whole refrigeration system is complicated and is based on the mixing of two isotopes of helium, helium-3 and helium-4. So in this mixing chamber plate, we reach 10 millikelvin. So 10 milli-degrees above the absolute zero, which is the coldest place in the universe, okay? Not even in space, it's that cold. And we have this in our lab in Trento. So if you come, you can see the coldest place one of the coldest places in the universe. So we have the fridge, and then inside the fridge, what we have? We have a lot of wires. All these wires that you see go from the highest part, so the room temperature part, down stage by stage till the coldest part at 10 millikelvin, so 10 milli-degrees above zero. And then if you zoom in among this forest of cable, you don't basically see in this picture, but that's where our quantum processor stays, where it's placed. So where our QPU, quantum processor unit, is placed. So this is the second take-home message. When you see this picture, this is not the quantum computer, this is just the fridge. The quantum computer itself is a very small chip that stays down in the cold. And this chip is actually not that different, if you look at that, with respect to the chips that are in your laptops or in your washing machine or in your smartphones. It's always a silicon or sometimes sapphire substrate with a circuit on top. But the fundamental difference is how this circuit works. It's not based on what we call classical electronics, so like semiconductor or transistor-based electronics, but is based on electronics that relies on the laws of quantum mechanics. And that's the rest of the talk, basically. So the question is, okay, we understood how it looks like, we understood the small chip, that's where the magic happens, okay? But how can we actually build that chip? How can we build a quantum computer? To answer this question, let's step back, and I think all of you are familiar with the concept of bits. The bit is the, let's say, unit of information in a classical computer, and all of you know that our classical computer works with some binary calculations where each bit can take only two values, 0 or 1. It's basically a switch, right? That's also why it's implemented physically. We have these transistor chips that can assume only two values, 0 or 1, or if you want, on and off, if it's a switch. Or let's use another metaphor for now, it's useful. If we take our globe, so like Earth, we can say if we have a classical bit, this bit can take only two values that we can map on the North Pole and the South Pole. And we say, just by convention, our North Pole is 0 and our South Pole is 1. And there is no other point that can be taken by the bit, okay? Now, the fundamental difference with a qubit, so a quantum bit, is that a quantum bit is able to take any value. So if we imagine this globe of our Earth, it's like if a quantum bit can live in any spot on the planet. And what is the physical meaning of the spots that are neither South Pole nor North Pole? They are a superposition. And here we go back to the famous Schrödinger cat that I think all of you have heard of. So for those of you who haven't, Erwin Schrödinger is one of the fathers of quantum mechanics, and at some point he taught this very funny let's say, mental experiment. It would be Gedankenexperiment in German, where he thinks, okay, let's assume that we have a cat, but this cat is a quantum cat. So it's a cat that doesn't obey classical physics law, but obeys quantum mechanics law. Then we take our quantum cat, we put it inside a box. We attach inside the box a system that releases a poison, but this system is connected to a decay of a radioisotope, so we don't know when this happens. And then quantum mechanics tells us that until we don't open the box, the cat is in a superposition of being alive and being dead. When we open the box, so when we do our measurement on the system, then we will find it either alive or dead, with a certain probability that depends on the state before. So these points that are neither North Pole nor South Pole, they are a superposition that have a certain probability to be measured then in the north or in the south. So when you open the box, when you measure your qubit, when you look at it, you will always find it either in the North Pole or in the South Pole. But during the calculation, you can prepare the state of your qubit such that is, for example, on the equator, which will be a superposition with 50% of probability to be found as 0 and 50% in 1, and so on and so forth. So this is the fundamental difference with respect to classical computing or classical bits. I use this Earth, this globe, because it's easy to explain, but actually we, in our labs, like physicists, use exactly the same logic. We use a sphere. It's not Earth, it's called block sphere, but it's just a sphere that we use to represent the state of our qubit. And later, in the talk of Enrico, you will really see how this works. But you see, for example, in this case, we have an arrow pointing towards 0, so this is a representation of a quantum bit, a qubit, in the state 0. And doing operations with qubits, what we call gates, is nothing else than changing the position on this block sphere. So rotate these vectors, for those of you who are a little bit more familiar with this, rotating this vector in a different position. And to do that, we have to interact with our qubit, and as we will see later, send some electromagnetic pulses that move and change the state of the qubit. So quantum computing is all about engineering a qubit, so engineering something that behaves as this sphere with a 0 and a 1 and superposition, being able to prepare a certain state, and then make it rotate to implement gates. And then, of course, as you will see later, you will not to make a quantum processor unit, you don't need one qubit, as you can imagine, but many qubits that need to talk to each other and being connected also by entanglement. But you will hear about that later on in the second talk. Okay, so we are done, right? We know how to make a qubit. But the question is, physically, practically, how do we make one? How do we make an object that behaves like this sphere that has a 0 and a 1, and I can make superposition? We need two ingredients. We need something that has two levels, so some object, something that has a 0 and a 1, and maybe more, but at least two. And we need to have something that can have quantum superposition. So how do we do that? Well, luckily, already nature gives us many things that can be used as a qubit. For example, if we think to atoms, quantum mechanics was introduced to also to understand the reason why, for example, the hydrogen atom, that you will see also later, emits energy in a quantized way. So energy is not continuum, but is discretized. So atoms are objects that have discrete energy level, more than two, actually, many more, but we can just restrict ourselves to the first two. So we have what we call ground state, so a state with lower energy. We have a first excited state, and so on and so forth, with this orbital of electrons around an atom that probably you have heard about. And atoms are small enough that they behave according to quantum mechanics. So if we are able to isolate one atom, and we are able to control the energy levels of these atoms, we have a qubit. We can also use photons. Photons are the particles of light, so the quanta of light, electromagnetic waves, also they're quantized. And photons have several properties. For example, they have a polarization. I think all of you have these sunglasses that if you rotate, you look at a screen, you don't see anymore. Okay, this polarization is basically the direction or the direction of the propagation of an electromagnetic wave. And photons can have, for example, two polarizations, and photons are quantum mechanical objects, so I can have a photon in a superposition of two polarizations. So if I map to one polarization my 0 and to another polarization my 1, and I have superposition, this is another qubit. So we can have a photonic qubit. And then, for example, we have electrons. Electrons, fundamental particles that you know because they're, for example, part of an atom. You have a nucleus and electrons around. They can also, of course, exist in other forms. Electrons have a property that is called spin, which is basically a magnetic moment of our electron. We typically talk about spin up and spin down. You can imagine as, if you want, a small magnet that points into different directions. So electrons can have spin up and spin down, and then electrons, again, an electron is a quantum mechanical object. So I can have an electron in a superposition of spin up and spin down. So an electron is another qubit. So you see, actually, already we have a lot of, here I call them natural qubits, that are just available in nature. This doesn't mean that it's easy, because you need, for example, to take a single electron to control the spin of the electron, to prepare it in a superposition. So it's, let's say, from the conceptual point of view, easy, but from the actual experimental point of view, complicated. But these are all qubits that we are, for free, already present in nature. But I'm a big fan of artificial qubits, because these are the superconducting ones. So the idea is, okay, nature gives us some qubits. They are there. They are okay, but we cannot change them, right? If I take, for example, one atom, it will have that energy levels, and I cannot modify it, because that's how nature made it. But if I'm able to make a circuit, that's totally artificial. I can design my circuit as I want, and I can make something that we even call sometimes artificial atom. Superconducting qubits, like transmons, are often called artificial atoms, because what happens is that I design a circuit, I go to the clean room, I make the circuit, and this circuit will behave like an atom, but I can artificially and arbitrarily decide where to put my energy level and how to engineer my circuit. And in that sense, it's much more powerful than natural qubits that they are as they are, and we cannot actually modify them. So this is, let's say, a second category where the main actor is actually superconducting circuits. But in general, it's like homemade qubits, artificial qubits. So since we have different types, as I show you, of qubits, so different way to implement a qubit, we also have a sort of zoo of quantum computers. So we don't have one way to make quantum computers. For classical computers, there is basically one technology, that is semiconductor electronics. But for quantum computers, we do not have a winner yet. We have around many different research laboratories and even research or R&D teams in big companies like I don't know, IBM, Google, Rigetti, many others, that develop quantum computers that are based on different types of qubits, and therefore they are completely different computers. The first one is the one that we already look at. So in this case, it's the Google superconducting quantum computer. So again, this is the big fridge, and then the chip down there. But for example, we can also have photonic quantum computers, and they work completely differently because we don't need to cool them down. And they look more like big optical tables with lasers and a chip where light can enter, and we basically make on the chip some sort of streets. We could call them waveguides, where the light can propagate and exchange information. And this is a photonic quantum computer. Then we can have spin quantum computers. I told you electrons have spins, this magnetic moment, and then if we are able to isolate a single electron, we can make a qubit out of it. And that's what we do with this kind of chip. These in green are gates that are able to make a potential such that a single electron will stay there, isolated, and then we can control it. Also in this case, we needed to cool it down, so we have a refrigerator that is one-to-one the same with respect to the superconducting quantum computer, but the chip is fundamentally different. And a last example that I want to give you are trap ions. I told you that atoms are good qubits, so if we are able to take one atom, in this case one ion, trap it in an electromagnetic trap field, and then control it, we have yet another type of computer, so-called trap ions. So you see, we have a zoo of different type of hardwares that can be used to make a quantum computer. Okay, so go back to the superconducting one, because I told you I would have advertised mainly that. So superconducting qubits, also known as artificial atoms. Why? Let's go back to the origin of quantum mechanics. As I told you, one of the big puzzles that physicists were trying to solve is why, if we look at the emission spectrum of an hydrogen atom, so if we look at the light that is emitted by an hydrogen atom, I don't see a continuum, but I see some discretized spectral features. The reason is because if I model my atom, I see that I have discretized energy level, and each of these transitions will give rise to one of these lines. And as you can see, they are not equally spaced. The distance between the ground, so the lowest energy, and the first excited state, so the first highest energy, and then to the second, third, and so on, it gets smaller and smaller. So we talk about anharmonicity, because physicists like to model everything as a quantum harmonic oscillator, and this is not harmonic, it's anharmonic in the sense that these discretized levels are not equally spaced. And this is very important to make a qubit. I'll tell you in a second why. But here on the right, you see the energy level, number 1, 2, 3, 4, 5, 6, and so on, which are not equidistant. Why this is important to make a qubit? Because I told you before that our qubit should have a 0 and a 1, and we don't care about the other levels. So ideally, we would like to have an atom with only 2 levels. In reality, we always have many levels, so we isolate only the first 2 true, in the sense that we decide to forget about the other ones. And we call computational basis the first 2 levels that we use for our computation, 0 and 1. But the number 2, 3, 4, and so on are still there. And the fact that they are not equidistant is fundamentally important, because if we send, let's say, an energy input to excite our energy level from 0 to 1, we have this distance in energy, and this distance is different than the next one. If they were all the same, when we send in an input of energy, we will excite from 1 to 2, but also from 2 to 3, to 3 to 4, and so on. So the fact that they are not equidistant gives us the flexibility to address only the transition that we want between the first and the second. Okay, so this anharmonicity is a fundamental property to make a qubit. And atoms already have it. Now we want to do it with circuits, so artificially. So what is the simplest circuit that we can make? An LC oscillator, for those of you who have done a little bit of electronics. So an inductor L, a capacitor C, so two, let's say, circuit components. And this is a resonator, so an oscillator, that will have energy levels that are equidistant. So the distance between 0 and 1 is the same than 1 and 2, 2 and 3 is harmonic. And this is not good. So this is not a qubit. We need to make a small change to make our superconducting qubit. That is the following. We replace our inductor with an element that is called Josephson junction, which is that orange cross that you see in the circuit on the right. And this Josephson junction is a very basic element in superconducting circuits. It's a little bit like the transistor in semiconductor. I don't have the time to explain you how it's done, but effectively it behaves as a non-linear inductance. So it modifies our potential such that our energy levels are not equidistant anymore. So you see on the right, the distance between 0 and 1 is bigger than between 1 and 2, which is bigger than 2 and 3, and so on. So we have made our LC circuit anharmonic. So the one on the right, it's a qubit. And indeed, this simple circuit is a transmon qubit, which is nowadays the most used superconducting circuit to make qubits. So it's nothing else, in force approximation, than a capacitor and a Josephson junction in parallel, which make an anharmonic oscillator or resonator. How does it look in reality? This is an example of a superconducting chip. So it's made on a silicon substrate. So below you have really a silicon chip, like a standard one. And why silicon? Because semiconductor industry has already developed so well silicon wafers that we use them, but there is not another fundamental reason why we have silicon below. We don't use it as a semiconductor. For us, it's just a base, a substrate where to make our circuit. And then on top, this will be a top view, you have here in light gray, aluminum. I told you aluminum is a superconductor, and indeed it's the most used superconductor with a critical temperature 1.2 Kelvin. And in dark, or in black, is the substrate below. So we remove the aluminum where you see dark, and then we have different elements here. So let me walk you through. This cross that you see, and probably you have seen also in some other pictures of famous, let's say, qubit design, is a so-called X-mon or cross-mon, which is a type of transmon. So the cross is just the capacitance. If we go back here, oops, sorry. The cross is just the capacitance C that you see in the circuit diagram on the right. And this is implemented just as a cross, where you have a capacitance between the inner part of the cross and the aluminum around, which is your ground. So that's the C, the capacitance. Where are the Josephson junctions? Where they are super small, you don't see them, but they are down here. And in this case, we don't have one, but we have two Josephson junctions, because this is a trick to make our qubit tunable, where we can basically decide the frequency of the qubit by some tuning. So that's our transmon. I didn't put a scale, but we're talking about hundreds of micrometers in the typical size. And for the junctions, we're talking about less than 1 micrometer square, okay? So very small objects. Then what else we have? In blue here, this serpentine, it's a readout resonator, because in the end of the day, you want to see what is the status of your transmons. You want to measure if it's a 0 or a 1 and make some statistics. So what we do is we have, this is a coplanar waveguide resonator, so a resonator with a resonance frequency in the order of gigahertz, so microwave. And it turned out that the state of the transmon will change the resonance frequency of the resonator. So if you are able to monitor the resonance frequency of our serpentine-like resonator here, we see if the transmon is changing state. So it's our readout system. And this is then connected here. This is the end of the chip, which is then connected to all the electronics and so on. Then we have something that I call qubit drive. This line here. This is the line that makes us control the qubit. Sending certain pulses, very highly engineered microwave pulses through the qubit drive, makes our arrow in the block sphere rotate. So it's a way to control the state of our qubit and to prepare it in a certain state. And finally, I have this last one on the right, flux bias, that is for this tunability that I talk about. This is just a way to change the magnetic flux between the two junctions, but here we go a little bit technical. It's basically a knob to tune the frequency of my transmon. So it's as simple as that. This is one superconducting qubit with one of the most commonly used geometry. So let's put everything together for our building instructions. So we have the chip, this one, that looks like the one that I show you. Here you don't see, but you have all these resonators, the transmon, the drive lines, the flux lines, and so on and so forth. That's the chip on a piece of silicon. This chip is packaged inside some packaging, microwave, such that we are able to send in and read out microwave signals that are used both to control the qubit and to read out the state of the qubit. Then we need to cool down. So we take our chip in some holder and we put it in our refrigerator, in our fridge, in the lowest part at millikelvin, about 10 millikelvin, down here. And then we still need to read it out. So there is a lot of cryogenic engineering in order to have some cables that do something that might sound easy, but it's not. There are cables that go from room temperature, so 300 Kelvin, down to 10 millikelvin, and we need to take care about noise, thermal dissipation, signal attenuation, and so on and so forth. So there is a lot of cryogenic engineering in that. And then once we have our signal out at room temperature, this is connected to a rack with some microwave instruments, for example, signal generators, vector network analyzers, for those of you who are familiar with this, that are used to send in signals and read out signals to control and read out our qubit and, in general, our quantum processor. So this is a typical rack that you will see with the microelectronics next to the fridge. And then on the right, once more, the true picture of, in this case, is the IBM quantum computer, but as you can see, it's very similar to the Google one. So, to conclude, citing one of the most famous physicists, Richard Feynman, in the 80s, so long ago, he was already saying nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. And in fact, more than 30 years later, we are still developing quantum computers prototype. We are getting close, but it's still an active area of research. Will quantum computers change our life? I don't know. You will maybe have the answer after the next talk. But I can tell you that a lot of practical problems that require optimization of difficult tasks and so on, for example, in cybersecurity and cryptography or weather forecasting, where we have a chaotic system to model, or even financial modeling, logistics, and so on, will probably be tackled better by some ad hoc quantum algorithm, but algorithm is not my expertise, so Enrico will tell you more about this. I conclude showing you our small contribution here in Trento and with my group at Fondazione Bruno Kessler. So we do make some of these superconducting circuits. We have a clean room where we can really fabricate them. And I brought you one that is here. I think it's exactly the one of the picture. It's here. So later in the networking part here outside, I'm very happy to show it to you and let you touch it. It's a test chip, so you are allowed to break it. And so we make our chips. They look like this. So here you have all the elements that I showed you before, these Josephson junctions, resonators, aluminum parts, and so on. Then we package it in these microwave packages. So these are the two ports where we send in and read out our microwave signals that tells us what the qubit is doing. And then we have our refrigerator. It's a little bit smaller than the Google one, but it's same brand. This is our mixing chamber, and here is where we put our chips. And these are two of my PhD students working with our fridge at 10 millikelvin. If you are interested in visiting our lab, we are more than happy to welcome you. So just write me an email, and later I can tell you more about this. And with that, I thank you for your attention, and of course, I'm open for questions.
watch out in offering to everyone, to all the room, to come visit your space in FBK.
Not at once.
But we might organize something with Speck&Tech.
Absolutely.
How about a journey, a Speck&Tech trip to FBK clean room? Yeah?
Absolutely.
More on this later. A couple of questions. Yeah, the first question was actually if there is a possibility to visit. You said yes. If you want to organize it by yourself, you can email Federica. Watch out. Otherwise, we will organize something, of course. Some questions that I will ask you will be probably answered by Enrico in the second talk, but I will ask them anyway, because I think they give a different point of view that might be interesting. So first one, what can we do with quantum computer? For which operations are used now and in the future?
So this, I think I answer in this slide here. So again, I'm not an expert, and I think Enrico can answer much better than I can. But in general, optimization problems work very well with certain type of quantum computers. Nowadays, I think there are groups working, for example, on chemistry and drug discovery. For example, the folding, again, I'm not a biologist or anything with bio in front, but I know that folding of proteins is something very difficult to model and to compute, and they are trying to use quantum computers, for example, for this. And also for, of course, cybersecurity and cryptography. I think this was covered, if I remember correctly, in a talk of Speck&Tech. So go back to the YouTube channel and have a look at that.
Yeah, good point. How many quantum computers are there in the world, actually?
Oh, that's a hard question. So I would say there are big groups and small groups. If you count only the big groups, like IBM, Google, and so on, not many. I think most of them are in Europe and America, even if China and Japan are now, China is now, Japan was already very developed, but China is now developing a lot. To give you a number, I don't know, in big groups, we are in the road of tens. Small groups, we are maybe 100, but not that many.
But all of them are in the sort of 4 different types, more or less?
More or less, yes. These
Okay.
are most of the most common ones, yes.
Why are all the layers at different decreasing temperatures needed instead of having only one layer at 10 milli
Oh,
K?
that's a very good question. For that, I will give now a 1.5 hours lecture on the dilution refrigerator. No, kidding. So let me go here. Oh, I have a picture. Yeah, let's use this one. No, this is a bad one. Let me, 1 second. I have a good one at some point. Ah, the very first one. Here, okay. So, why? Because the way this guy cools down, it's very complicated. We have 2 main phases. The first phase is to bring the whole system at about 3 or 4 Kelvin, and this is done with a mechanical refrigerator, so-called pulse tube, which is basically based on some thermodynamical cycle where moving a piston, you manage to remove energy from the system. If you go to our lab or any other lab, you will hear this very annoying sound like ch-ch-ch-ch-ch. That's a pulse tube that brings you at 4 Kelvin. And once you are at 4 Kelvin, the actual dilution starts, and then you have a mixture of helium-3 and helium-4 that is running in some tubes that now are hidden behind the cables. And you cannot go directly to 10 millikelvin. You need the one plate, this one that is called steel, where you are literally distillating some helium-3 and make it circulating. So this has to stay at 700 millikelvin because it's the temperature where you can evaporate helium-3. And then the actual refrigeration happens here, where we have this mixing chamber, where you have 2 phases of helium-3 and helium-4 separated. And basically, atoms don't like to move through the transition. If you force them to do that, they require energy and they cool down. And that's the reason why we can reach 10 millikelvin at the dilution refrigerator, at the mixing chamber state. But that's a complex topic, so I would suggest you to talk to me later again.
All right. Yeah, it's a subsequent step.
Yes, exactly.
Going down. So qubits still end up as ones or zeros, right? So what's the real advantage? Qubit seems like a very complicated way to get the same computational item used nowadays.
That's a question for Enrico, but the answer is in between. The algorithm is fundamentally different because you can, during the operation, you can actually exploit the superposition. So during the operation, you have these gates that exploit the fact that you can be in superposition only in the final measurement. You are in 0 and 1 with a certain probability. So if you do a statistical measurement, you will find n times 0 and n times 1, and from that is, let's say, the end of your algorithm. But the advantage comes from what happens in between.
All right. Is there any advantage or limits with using artificial qubits over the natural qubits?
The fact that you can write down on paper how you want your energy levels to be. So literally what I do, I mean, with my team every day is writing down an Hamiltonian, so let's say a physical description, and I decide where are my energy levels, and I make the circuit as I want. With natural qubits, that's not possible.
All right. Are both qubit drive and flux bias influencing the qubit in the block sphere? Why do we need both?
No, they are not both, and this maybe I was not clear. So the drive is the only part that does this. So to do this rotation, what you do in practice is go to your circuit. That is, this is counterintuitive for me. This, yes, here. So this drive line is the line that I use to send electromagnetic pulses that rotate the vector in the block sphere, so it's what controls. The flux line just choose a working point for the qubit. So it's like if I can decide the frequency of the qubits, then I send a steady current in my flux line, I fix the working point of the qubit, and then I make it rotating on the block sphere using the drive. So there are two different functions.
All right. There are many more questions that are coming, and I think some of them can be asked directly to you.
Absolutely.
Especially very technical ones about implementation, chip production, etc. Probably the last one I would like to ask you is, how is the quantum computing influencing AI? And why big techs like OpenAI and Anthropic are not investing heavily in it? Yet?
That's a difficult question for me. So I know that quantum computers can be a platform for AI. So people start to talk about AI quantum, but again, I'm an hardware person, not an algorithm person. But I can tell you that big companies are investing in that. For example, Google has Google AI and Google AI Quantum, and the two teams are actually working together. Of course, on the everyday challenges are very different because the first one is on hardware, the second one is on software, but they are investing on this. Definitely.
All right, then more questions about implications and future outcomes on Enrico.
Absolutely.
Thanks a lot, Federica.
Thank you.
Okay. All right, let me go back to the previous. Hold on. Okay, momento spoilerini. It's the 29th of June, but we have still a part of the season that is coming. We're going to have another event before the summer break, and we will be back in September and October and November and December, so a lot of events for this 2026. But how do we decide them? This is a picture from our event in March where we celebrated our 10 years of Speck&Tech. And as you can see, there was a lavagna, a whiteboard, where people at the end of the event were actually sketching on it, taking notes, memos about interesting events they would like to listen to. And this event on quantum was actually, because one of the most interesting and upvoted questions was, I would like to listen to a talk about quantum and se il quantum sarà la prossima bolla dopo le AI. So this was the reason why we organized this event, actually. And I was like, okay, we don't even know if AI is a bolla at the moment, but yeah, let's take it for granted. Second thing, the second most asked topic was about AI, LLMs, AI agents, and we're actually organizing an event about it. So either it's a quantum date, as you see. So it can be either on the 22nd or on the 23rd of July. Last event of the season, we're going to have this event about AI and us. So how LLMs and agents and new technologies are influencing our behavior and how we are approaching them and giving them prompts and improving especially our way of learning and getting and understanding new concepts. So this is going to be on the 22nd, 23rd. We will be publishing it either this week or the next one. Okay, I'm stopping this joke. Anyway, next days, stay tuned. These are the dates. It depends on the availability of the venue and the speakers.
And one of the speakers might or might not be in this room.
Oh yeah, no, good point. Yeah, yeah. All right.
Yeah, so that's our next event. But as Franz was saying, we have events booked, or at least ideas, until the end of the year. The next one, actually in September, will be about a topic that we never touched before. It's about refugees, migration, and we have some very heavyweight speakers from actually the United Nations High Committee for Refugees, UNHCR. We will talk about how technology interacts with this important topic, which is something that is, something that is very much talked about, but probably not very in very like productive ways usually. So we will see what people are actually doing to help other people, and using technologies, using AI, of course, as we do at Speck&Tech.
We cannot tell you anything more, but the date is set. So 30 September, save it on your calendar already. And last one, already selected, a heavy, hard topic. On the 19th of October, we're talking about cancer. It's a word, especially in Italy, that nobody likes to mention, so I will say it in Italian, that can be either cancro or tumore. And especially AI, but in general, the new technologies are making a dramatic change in the research of cancer cells and the way we are treating, and we are creating new mechanics and new ways to tackle cancer. It's going to be a crazy event, absolute. I don't know. I don't want to spoil it too much, but anyway, we will be at Muse. We expect il pubblico de grandi occasioni, hundreds of people, and it's gonna be.
They asked us, like, how many people will you have because the fees for fiscal reasons change? We said, yeah, hundreds.
Yeah.
Go for the big number.
And it's gonna be quite crazy. We're gonna have a piece of theater, just to tell you.
Yeah.
So there's gonna be a very tech talk and a piece of theater, something that we've never done before, of a show. So it's going to be quite cool. Save it on your calendar. It's already set again at Muse.
Yeah.
All right. One more thing.
Yeah, one more thing. So Franz said we're going to have still one event for the season, but actually it might be two events before the end of the season. And there is a comeback that some of you might have seen coming, some of you not. It's something that we last did, I think, 3 years ago.
Yeah.
It took a long break, but either on the 18th or on the 25th of July, and that's not based on quantum, that's based on the weather, which is even more random, more difficult to predict, maybe. No, just kidding. But yeah, Speck&Tech is coming back. So if you don't know what Speck&Tech was, or is going to be, okay. I guess some of you missed it. So Speck&Tech is where we take our community, take our friends, and we say, let's go up to the mountains. It was born when we were, after we were forced to stay home for a long time indoors because reasons. Then we said, okay, let's go outdoors and meet outside. And so we go to the mountains. And
yeah, a couple of good people, especially Alessio and Elisa, took this courageous decision of reviving tech, and we're taking it live. The QR code is already working. If you want to just save it on your calendar, get a ticket, of course it's free. We're going on a hike.
Yeah, we have already the path. We're going to Rifugio Lancia in Pasubio. Quick word of advice. If you never walked in the mountains, if you don't know what hiking is, if you don't have a pair of hiking boots, don't come with flip-flops or sandals. We don't want to.
It happened.
Yeah, we have guides this time. We are more legit than we were, but still be prepared. It's a walk in the mountains. It's a 4 hours walk, more than 10 kilometers with some ups and downs. So it's a walk in the mountains. It's not a walk in the park. We have also content there because we're not just taking a walk. We will have Augusto Ciuffoletti, a researcher professor, who's going to talk to us about sustainable digital signage for tourists and in like caves and stuff. Very
So
cool
basically, how to make new
Segnavia, yeah, guideposts.
Segnavia guidepost in the mountains with new technologies. And
that
actually,
work without internet and so on.
yeah, exactly. The QR is already there. There's all the description. There's all the tickets. You can just get your panini, your sun hat, your sun cream.
Places are limited because safety.
We meet here at Impact Hub and we go together. So we, if we even don't have a car, we drive you. So yeah. All right.
That's all.
If you're done it, we move on to the second talk. So Enrico Blanzieri on stage.
Hello, thank you. Thank you to the organizer for inviting me here in this very nice place and with a nice audience as well. So let's start. And we start now with the qubits. So I was so lucky tonight that we had Federica that talk about qubit already. So we know already a lot of things about qubits, and here you see also some, like, let's say, the mathematical way of showing a qubit that is basically the superposition between 0 and 1 with a couple of coefficients that are basically complex numbers. Okay, and the idea is that these numbers there with the modulus square gives the probability of actually measuring two things. Okay, so this is the qubit has come from physics and for the technology that builds qubits for us. But well, my background is electronic engineering, then I converted to computer science and basically need some kind of abstraction. And my favorite abstraction is the coin. So it's a coin, I'm flipping it, okay? And my way of seeing a qubit is basically the coin when it's flying. So you toss it and you think of the qubit with the coin is flipping there. It can be 0, 1. It has some probability of being 0 and 1, okay? And if the coin is fair, the probability will be half and half. And what is nice about the qubit is basically that you can manipulate the probability of the coin to be head or tails while it's flying. So this is the main things that I think when I think of qubits. So here's the block sphere. There is some more mathematics. So the idea of the block sphere is basically you represent the points over the sphere in spherical coordinates. And basically the idea, as was already said by Federica, is that you have the 0 there, the 1 above, but you can have also all the other possibility. And actually, each of these positions will have some probability. There are places on the sphere in which actually the probability of measuring 0, 1 is the same. I mean, there are some kind of invariant places in which you still have the same stuff. Okay, and now you have the possibility of manipulating that. Federica showed us how to do it with the superconducting qubits. But here is a graphical thing to say that manipulating a qubit means basically to rotate it in the block sphere. So what you see here are, I'm sorry, I just went too fast. Okay. Here you see what is called the X gate. Basically, is a rotation about the x-axis, and the effect of that is basically that you invert the 0 on the 1. So it's basically is a kind of knot from our point of view. There you see something similar. That is, I'm sorry, just not good enough for that. Okay, this is the square X, in which instead of rotating of p radians, you just rotate of p half radians. And the effect of that, you see, is that the position is basically sent from being on the North Pole to be on the equator and the other way around. And this really changed everything because it means that when you are measuring it, the probability of measuring 0, 1 will be, let's say, basically by chance. It would be like the coin that is flying. Okay, these are not the only gates that you can have. We saw the X, but there is also the Y and the Z. They are the so-called polymatrices that are basically the rotation around also the other axis. And what is interesting is that they are rotations, so one can compose the rotation and obtain other rotations. So this means that the rotation around the axis Y can be seen as a combination of rotation about X and around the Z axis. Okay, once we understood that the manipulation of a qubit is just rotation, one can think that one would like to rotate it in an arbitrary way. Well, it's actually possible if one had the possibility of rotating it along the 3 axes with different rotation. Okay, so here you have the rotation, each of them is a parameter, and this means that one is able to get back to the actual rotation that one has done. And so we start to see how with some elementary kind of things one can obtain all the rotation that one would like to have. Okay, what is also interesting here is to see that it's also possible to obtain an arbitrary rotation by composing rotation around the z-axis with some parameter and rotation of p half with the square x. So in other terms, it's enough to rotate around the 2 axes for obtaining everything. Okay, and finally, we see what is an important gate. It is so-called Hadamard gate, and it's just a rotation that basically, again, like the square x rotation, move the state from the poles to the equator, and in this way, one has obtained again a situation in which the probability is, let's say, is distributed over the possible things. Okay, I think we more or less learn what to do with the 1 qubit. So we know that it's possible to rotate. So now let's start to have 2 qubits. So 1 coin on one and 1 coin on the other. And then we can ask ourselves, what can we do with 2 qubits? Well, the first thing is that we cannot copy 1 qubit in the other. So qubit is such that we cannot do it. So there is a theorem that within quantum mechanics that say that it's impossible to copy an unknown quantum state in another one. So this means that something in which we are really familiar with, that is copying information, copying a bit, it's not possible to do it with a qubit when the qubit is in whatever possible state that it has. Okay? So this is the first things that we have. So the things start to get a little weird. And but what happens is that it becomes even stranger. Is that instead of having just 2 coins, we could have each of us can toss a coin. I don't want it to do it, but it's okay. So if one wants to have his own coin and tossing it like that, you can start to imagine that we have the room full of coins that are flying. Well, if this coin were quantum, chances are is that they interact one each other. Okay, and so if you start to put quantum system together and considering as a more complex system, they basically become a multi-body system or multi-qubit system, and something starts to happen. The first thing that happens is that the state space, oh, that is, why is green the light? The state space grows exponentially. So this means that if you have 1 qubit, we have 2 states, 0 and 1. If you have 2 qubits, we have 4 states. But if you have n qubit, you have 2 at the power of n states. So the states grows exponentially. This is the first things. And then it also happens, a thing that is called, I'm sorry, is called entanglement, that say that this part, these coins, let's say quantum coins, interact in a pretty strange way. It means that they start to not be independent anymore. So if we have a lot of coins that are flying, they are independent. Well, they can maybe, let's say, crash one against the other, but eventually they are independent if they are far enough. Well, in quantum mechanics, they can be actually dependent. And now we will see how we can do it, this dependency. OK, so enter the CNOT gate. What is the CNOT gate? It's the first gate that we see that comprises 2 qubits instead of just 1. So here are the gates we already see. This is the X, the Z, the Hadamard. And this is the description of the CNOT. Well, one can have of the CNOT a description that is purely classical. These are the things that you see here. So the idea is that one has 2 bit or qubits. One is control and the other is target. So if the first bit or qubit is 0, the other is unchanged. Whereas if the first bit is 1, the other flips. So this is the input, and this is the output, is flipped. OK, these things can also be defined for a quantum gate. Why? Because quantum mechanics is linear. So this is a base. So you are basically represented how a base is transformed into vector into vector by the gate. And so in this way, you can really extrapolate the behavior that the system has also for the other state. So you can basically linearly represent what's going on in the middle between these things. And so you have this CNOT. And now let me show you what the CNOT does. But for showing it, I want to say that one, let's say, way of doing quantum computing is basically to do this circuit-based computing. That means that one take, let's say, somehow seriously the fact that the things that one can do to a qubit or to a couple of qubits are gate. In reality, they are not gate. We have seen that the circuit are not this kind of stuff. So the gate here are the procedure that one applied to a physical system. And eventually, one measured it in order to obtain some kind of effect. The idea is that one would like to keep this system coherent and not try to have less interference as possible. But what you see here is the interface of the IBM quantum platform. You can actually access to that if you want. It's just a matter of have to define some password and do some authentication and so on. And let's say for 30 days for free, you can play around with these things. This is called a composer. And you have here a number of qubits. You can actually add of them. Here are just 4 of them, but you can add up to 156 qubits. And you can start to put here gates. OK, for example, here I put this is not really a gate, but well, it's a procedure. So this means that this qubit is set to the reset, to the value 0. And then I apply an Hadamard gate. That is the one that rotates from 0, 1 to the equator of the block sphere. OK, what happens here, I hope that you will be able to see it, these are all the possible combination of these qubits when one is measuring it. And when you see that it has the same probability of measuring 0, 0, 0 or 0, 0, 0, 1, this means that this Hadamard gate makes the probability of measuring 0 or 1 in this first qubit equal. That is something that you can also see here. Now, let's play around again with this system here, and we put there the C naught. Okay, the C naught is this thing. So I connected together these two qubits with the C naught. So it means that this is the control, and this is the things on which there is an effect. And what I see that is here is that the probability of measuring these things is becomes different, okay? Because now the probability is either on measuring both the qubit to 0 or both the qubit to 1. So in other terms, I entangled these two qubits. And then they are, let's say, constrained to have the same value. Well, to have the same value when I'm measuring them, not before. Before is just a matter of probability. And what is most interesting for me in this system is to add another things here. What I had here afterward is a knot. So this is the X rotation. So I apply a rotation from the North Pole to the South Pole. And what you see here is that now, again, I'm really sorry about that. But what you see here is that now the two qubits, when measured, are constrained to be different. So because here the probability is 0.5 of measuring 0.1 and 0.5 to measuring 1.0. Okay, but what is nice here for me as a computer scientist is that the fact that I put a knot in this qubit has effect also in the other qubit. Okay, and this has happened after the C naught. So this means that this entangled is such that an operation that I do on that qubit has an effect on the measure of the other. Okay, so this is really a way of seeing entanglement working in a computer. Okay. Now let's move on. Okay, so we said before that when I start to have a lot of qubits, a lot of coins, I have this space that becomes bigger and bigger. And basically the idea is that that quantum computing could be useful if we are actually able to use at least some part of this huge space that is exponential in the number of qubits. And this is basically the challenge that we have and the people that start to work on quantum computing actually had. Okay. Now I will show an algorithm, a quantum algorithm that is a Grover algorithm. It's not a new algorithm. It's actually very, very, very old. It's something that goes back at least in the 90s. And it's interesting because it's quite a strange thing for a computer scientist. So the first thing is a task. Even the task is not easy to understand for a computer scientist. So people in the quantum computing community call it the unstructured search. So the idea is that one has what they call a database of n elements. So the database is kind of strange things again for me. And basically, only one of these match a condition that fx is equal to 1. In other terms, you have an oracle. So you have a function that once it's fed with this data, say that, well, I found it. And the other is always 0. Okay, what is the idea of Grover algorithm? The idea is that given the fact that we can put in superposition all these things, is there a way of using this oracle in a way that I can found this element without actually apply the oracle for all the possible points that I have? In other terms, the idea is that can I do better than actually having to look at and apply all the points to all the possible x to this f, okay? The idea is to try to show that it's actually possible to do better than looking all of them. How this is done? Oh, okay, it's done in this way. There are two main things to do. There is an oracle call and a diffusion operator. And the idea is that you have a first layer in which you apply the Hadamard gate. Remember, the Hadamard gate is the things that basically build the superposition. Okay, then there is and this is the superposition that is built. Then you have this oracle that is a function. This is basically a quantum circuit that we know that will basically just respond to 1. And then you have what is called a Grover iteration. That again, there is still Hadamard everywhere. And there is something that we will see is basically a rotation. And both of these two operations are rotation in practice, because the oracle will actually change the sign just of the target element, whereas the diffusion operator basically will rotate the amplitude around the average of the state as it is now. I know that it's not possible that is not possible to be clear here completely, but again, this is another way of seeing. So there are this diffusion part and this oracle part, and then a lot of Hadamard or gate everywhere, and these are the symbols for the measurement. And this is more or less the mathematical definition of what these things is done. So here you see there is this gate that basically is change the sign only of the x for which the oracle is 1, whereas the other basically change the fakes of everything with the exception of the things that are 0. So there are two kind of reflection. Okay, well, this is basically the way in which it works. So there is first the superposition, the phase inversion, the inversion about the mean, and the measurement. This is basically what is the way in which the things are done here. Okay, now some, let's say, abstract rotation. Okay, so this is basically the effect of the diffusion. So the idea is that one has, this is not the block sphere, this is this is just a plane. So the idea is that A1 is the vector that we would like to find, where A0 are all the other components in the system. So you can think that it's a vector space. You have these two vectors that are in two different directions. And so and the diffusion is done in a way that it actually moves the things around this axis that is the average. Whereas the oracle actually moves the things around the A0. So the idea is that, for example, one starts here, then is reflected on the other side by the oracle, and then this is reflected around these things by the other things. So eventually, what happens is that there is a rotation of the state towards the vector that one would like to find. So in other terms, there is a series of iterations that actually move the vector towards the one that actually is the one that makes equal to 1 the value of the oracle. Okay, what is the effect of that? After the proper number of iteration is that the probability of measuring the right vector becomes, let's say in this case, 1 order of magnitude higher than the other. So with some statistics, sorry, one is actually able to find it. Okay, in terms of complexity, the Grover algorithm is, let's say, it has a quadratic advantage. So this means that if one classically have to evaluate 1,000 of times this function, in just 32 steps, one can do it with Grover. If one has 1 million of things to check, with just 1,000 steps, one is able to get it. Okay, and this is the Grover algorithm. Well, actually, it has some problem. So the fact that there is the complexity of the oracle. So the oracle is a quantum circuit that one has to build. One could also wonder how can it possible that one builds an oracle for finding something that it doesn't know about? And then, well, there is overhead cost because one should correct the logical operation, but it is general for all the computer. And there is no exponential speed up because the speed up is just quadratic in this case. Okay, and so this is Grover, and we see it as an example of a quantum gate computer that solves this problem. Is the only way of doing quantum computation the gate-based model? The answer is no. There are alternative quantum paradigms that I'm going to show. And the first one is the so-called adiabatic framework. This is actually a bit complicated, but the idea is that we would like to move the system from a known situation to a situation in which the actual measurement of all the system drive to the solution. In other terms, one wants to move the system from an initial state to a state in which the so-called ground state is actually the solution of the problem that it has. Well, I'm not going into detail, just know that there are other ways of doing computation, and this is in general universal, and it resembles somehow what is called the quantum annealing, that is instead different. The idea is that in this case, one represents a problem with actually a lot of qubit. Okay, how much time do I have? Okay, because this is it seems that it's blocked. Okay, 5 minutes. Okay, quantum annealing is a bit different in the sense that it exploits the quantum tunneling effect. It's able to find the solution, and this is done basically for system that has, let's say, specific purposes. So here you have a paradigm comparison between the two paradigms. But what is important to know for us is that we saw IBM as an example of gate-based quantum system, quantum computer. Here we have the D-wave quantum annealer that has some advantage because the number of qubits is bigger. The problem is that they can basically solve just one kind of problem, that is this cube problem here. And there is actually the problem of initializing it. Okay, now let's see what happens now. So let's go back to our IBM system. And let's start to use it for real. So we have measures here. Okay, we have measures here, and here you see that the probability are not really exactly the same, because these measures here take into account the fact that the machine is not perfect. And if I actually run it on a system, so this is the output of a real run that one can do in this system, it happens a couple of interesting things. The first thing is that the circuit that is actually run on the machine is different from the one that I put inside. Why? Because it's been compiled in the kind of primitives operation that this machine can do, with a rotation around the z-axis and the square x, as was seen before, that permits to do all the things. And here this connection is connected to the Josephson junction that Federica was presenting. And again, the probability that should be equal, they are not really equal. Okay, what does it mean here? That, well, there is a problem with the actual computer. They are noisy, and they are not really doing what they should do. And so it's not really possible to do all the things that we would like to do with them. And this leads to the problem of what to do in this called NISC era, that means noise intermediate scale quantum computers. And what can we do in terms of application? So probably all of you have heard about the fact that there is this Shor algorithm that break cryptography. We had also a talk 3 years ago here at Speck&Quantum about that. We also hear that quantum simulation is probably the way to go. You see Feynman, so it's the same things that Federica was citing. Here we have an exponential speed up. What is the idea here is that quantum system requires this huge space. So if we have a quantum computer that is able to simulate a quantum system, this is probably the place in which there can be some kind of real application. And then there is also other things that can be done that are, let's say, optimization, quantum machine learning, and other things in which there is polynomial speed up with a question mark. So in other terms, we don't have here an exponential speed up, but we have a lot of things. Well, for example, Grover is one of the things that we have here as a possible things to do. So using in particular also the quantum annealer, is possible to optimize things. So these are the things that were already cited impartially by Federica as well. This is something that can be done with the current hardwares. It's possible to do quantum machine learning. There was someone that was asking about AI and quantum. So there are, let's say, things about quantum machine learning. So you had 3 years ago a talk about quantum machine learning. So I don't want to go in the detail here, but the point is that it's possible actually to build quantum neural networks to some extent. So I'm going to conclude just for saying what we are doing at DISY. Okay, we are doing some work on these things like weighted ensembles, that is quantum machine learning, optimization of circuit, and also quantum locality, with the idea of applying locality in the space of the data in order to increase the way, improve the way in which the system are working. Okay, we have also another activity that is Propero. Propero is the name of a startup, and we will basically start these things and do it for trying to do practical quantum optimization. And I think these are thanks to the people that work with me, both in the Future Startup and in the DISY QML. And these are the sources. And you see, here are my 20 cents, because it's a picture that I took over my desktop. Okay. Thank you.
Thanks for the talk, Enrico. And we have a few questions for you. So our audience is wondering, how far are we, or is it like, is there going to be something like quantum programming languages, and how's that going to look like to like program quantum algorithms? Is there going to be like Turing completeness type systems? Is that even something that makes sense?
Okay, yeah, it makes a lot of sense. So basically, what you have seen with this composer, with the qubit, is basically a quantum programming language. So the way in which one represents quantum algorithms, at least in the gate-based architecture, is that one. So this is the one, let's say, proposed by IBM, but definitely is a programming language. So they are not really gate. It's a way in which one describes the procedure. In terms of Turing completeness, the idea is that there is this notion of quantum Turing machine. There is like a Turing machine, but basically the control function is done by a unitary that is basically a quantum circuit. Plus, there is the tape is different in the sense that one has a kind of random access to the tape as well. So it's a probabilistic classical, it's like a probabilistic Turing machine plus the fact that you control it with a quantum unitary. But yes, these notions are well.
Cool. And that the example you've shown looks like very low level. Do you think there's going to be more like higher level languages to build these machines in the future?
Well, I don't know. I think that it's possible that there could be something like accelerators in the sense that you actually maybe program or an AI program for you, like it happens all the time now. And then the machine can be also an AI, recognize that there is a part that could be, well, let's say, deployed on a quantum machine, and that write the code for that part.
Okay, so like
this is
compiler optimizer kind of thing.
Yeah, exactly, something
cool.
like that.
We have other questions about more of the social impact of these technologies. So they have some potentially scary effects, like breaking cryptography or jeopardizing what we rely on for online transactions and so on. So how should we develop this technology responsibly? And also, what can we do to prepare ourselves for the disruption that this is going to bring, even in the terms of like what skills should we acquire?
Okay, so there's a very interesting question. Okay, I wonder myself why people should build quantum computing in order to break the cryptography. I think it doesn't make any sense. So I agree with some kind of wondering why when people should do it. Anyway, it's not the only things that quantum computing could do it. And so I think that the potential for application justify the risk or the fact that some kind of cryptography can be jeopardized. Anyway, there is an area so-called post-quantum cryptography, post-quantum security, that actually assume that the attacker is a quantum machine, and then try to devise protocols and system and cryptography that can resist to this machine as well. Okay.
Mm-hmm. And like for a random person in the audience who's wondering, okay, my life has just been disrupted by AI, and they say quantum is going to be as disruptive, if not more. How should I prepare? Is there something I can do to like be ready for that? Or is it too early and we don't even know how that's going to look like?
Well, I actually don't know. So actually knowing something more about it is a good way of being ready. So maybe playing a little with this system that permits you to understand better what it's got, it's a good thing. But anyway, I actually don't know if it will be so disruptive as AI is now, but also AI arrived in a very quick way, right? So so I think I don't know, but actually some responsibility. Well, on the scientists is okay, but in the public, I think has the responsibility of inform, and in a way that maybe also the decision makers are informed as well, even if it's harder, apparently. Okay.
Let's wish ourselves good luck with that then.
Yeah.
Okay. If you have more questions, there were a few more that, of course, we don't have time to ask all the questions. You can chat with Enrico later in the networking session. So another round of applause for Enrico Blanzieri.
Thank you. Applause for you.
All right. Wrapping up. So, in a few minutes, we're going to have Speck for real and cheese, and of course, veggie and celiac options. So, if you are celiac, find anyone from the organization. We also have like celiac and gluten-free food. There are carrots. There's non-alcoholic drinks. And there's, of course, Brewdog beer. So 4 different types of beer. If you're into it, going from left to right, from the strongest, the most IPA, the most lupolata, to the right, so the most basic, the lager one. Find the one you like the most. And also we have gluten-free and alcohol-free beer. So they should be quite cold, so you're gonna enjoy it. Cheers, of course. Differently from the other times, since it's the 29th of June, and I repeat it one more time, we're gonna do it outside. So at the end of this talk, you are gonna pass through the corridor, you're gonna end up in the kitchen, and in the kitchen you can get your food and go outside and enjoy the night with your poles.
Yeah, get the food inside and go outside to enjoy it.
Yeah.
So, you see this nice T-shirt that I have, that few people in the audience have. This is our 10th anniversary T-shirt, celebratory for our 10th birthday.
Something you should really have.
Yeah. As you know, or maybe you don't, we print the T-shirts once. Each year, we do a new T-shirt, a new design, and we don't do reprints ever. So, if you want to get it, you have to get it while we have them. And how do you do that? Well, outside you will find Sam with the desk, and you can buy the T-shirts. They are very nice. They have a print on the back and a logo on the front. And we also have some of the last year T-shirts, probably.
Yeah.
Some of the mountain T-shirts.
I guess like a couple of them.
A couple of the.
They range from XXS till triple L, like
Triple XL.
XXXL. So like,
yeah,
they
we have all the
fit
sizes.
almost every one of you.
Yeah.
Almost.
Yeah. So why should you get a T-shirt? Of course, because it's nice, but also because it helps run our events. It helps pay for the beers, the food, and everything else. But you can also help us a bit more if you don't want to get a T-shirt, or if you get a T-shirt and want to do something more. You can leave us some small donation. We don't need much, just a little bit to pay for your beer. It's not mandatory. You can take the beer and go. But if you want to be nice, and if you want to help us continue these events, just leave us some cash, or we also take cards, we take Satispay, so not having cash is not the excuse. Right.
All right, there is the last one, the last slide actually. That should be the way to restore this room, to leave the space to
normally we
drinks.
have to clean the space for the networking, but actually we're going to be outside.
This time is going to be even easier because we're going to do the networking outside anyway. If you manage to, you can stack your chairs if they're similar. So like these red ones, you can just put them on top. If you have like the foldable ones, just fold them and leave them on the side, and then you head to the kitchen. All right?
Yeah, but yeah, we're gonna move this out of the way and make our way to the networking outside.
And at this point, we meet you in 3 weeks for our next event about AI. Thanks so much. Enjoy the night.